Welcome back to Partial Differential Equations. I'm Dr. Jeff Groh. Today we're going to look at the applications of the Fourier transform. Before getting into it, I would like to point out the very close similarity between the Laplace transform that you learned about in an ordinary differential equations course and the Fourier transform. For the Laplace transform, you integrated from 0 to infinity your function e to the minus st dt, leaving a function of s. For the Fourier transform, we have an integral from minus infinity to infinity of our function e to the minus I st dt. You can see that these are very similar. The key property of the Laplace transform that allowed us to solve ordinary differential equations was that the Laplace transform of the derivative of y was s times the Laplace transform of y minus y evaluated at 0. In other words, the Laplace transform could, in essence, undo derivatives. The proof was very simple. It depended upon integration by parts, integrating out the y prime part in the integral, defining the Laplace transform, and taking the derivative of the exponential part, hence the s that appears here. The properties for the Fourier transform should be very similar. We'll begin by supposing that we have a function of two variables, x and t. And we'll look at the Fourier transform of the partial derivative with respect to t of u. We're going to assume that we're calculating the Fourier transform on the x variable. So I'll put a dot here. So in the end, what we get is a function of t, which is not involved in this Fourier transform, and s, which replaces the variable x. If you think about it, the derivative with respect to t has essentially nothing to do with the integral. And so we're integrating from minus infinity to infinity this partial derivative with respect to t of u. I'll say xt e to the minus I sx dx, since we're doing the Fourier transform on the x variable. This derivative with respect to t is applied to the u function. It could apply to the other factor as well. It doesn't really matter because it's constant relative to t, not having any t's up here. So the derivative could be thought to apply to the entire integrand. And it would be nice if we could bring the partial derivative out. Which then gives us the partial derivative with respect to t of the Fourier transform of u. In other words, the Fourier transform and partial derivatives with respect to t, the variable you're not taking the transform with respect to, commute. You can switch the order. That applies for most of the functions that you're familiar with, but perhaps not all. Interchanging an integral and a derivative implies interchanging two limits. And you'll discover theorems when you take a graduate course in real analysis that will allow you to do that. And you'll study the class of functions for which that is permissible at that time. So in a theorem, on important properties of the Fourier transform, number one will be the Fourier transform of the derivative with respect to t of u is the derivative with respect to t of the Fourier transform. The commutivity of the Fourier transform and the derivative with respect to t, the variable you're not taking the transform with respect to. As an immediate corollary, and due to math induction, we may deduce that the Fourier transform of the nth order derivative of u is the nth order derivative of the Fourier transform of u. Again, this is the variable that you're not taking the transform with respect to. What's even more important is consideration of what happens when we take the derivative with respect to x. How does that affect the Fourier transform? Does it work like the Laplace transform? And the answer is almost, except in this case we're integrating from minus infinity to infinity, and assuming that the function is integrable, it has to die out and go to 0 at the endpoints at negative infinity and infinity. Which means that we get I times s times the Fourier transform of u which is now a function of s as well as t. It follows immediately then, by induction, that when we take the Fourier transform of the nth order derivative with respect to x, we'll have is to the n, and then the Fourier transform, t, and then our function of s. The only property we really need to prove now is the property 3. So we'll take the Fourier transform of the derivative with respect to x of u and see what we get. This is by definition the integral from minus infinity to infinity of the derivative. I'll put an x here, e to the minus ix dx times s. Now, we use integration by parts, which means we have to assume that u is in the class of functions for which integration by parts is a valid theorem, which is not all functions. We'll assume that fancy u is e to the minus ixs and dv is ux dx. It follows then that d fancy u is minus is e to the minus ixs dx, and v is u. So it's going to be uv minus integral v du. I'll put the equal sign down here. uv minus the integral of, let's see, we get a minus is that can come out of the integral here. It's u of xt e to the minus ixs dx. Now, e to the minus ixs, provided both s and x are on a real domain, is a bounded function. It's bounded because e to the I theta is cosine theta plus I sine theta. So if we take the complex modulus of e to the I theta, we get the square root of cosine squared plus sine squared, which is 1. So complex numbers in this form always have a magnitude of exactly 1. What drives this to 0 is the function u. We're going to assume that u is integrable, which means that it has to vanish as you go out to plus and minus infinity. And that's why we get 0 for this first part. And that leaves us plus is times the Fourier transform of u. And that's the end of the proof. For our first example, let's apply this to the one-dimensional wave equation, which takes the form 1 over c squared utt equals uxx with initial data u of x0 equals u naught of x and ut at x0 equals u naught t of x. So we're defining the initial displacement and the initial velocity in this equation describing accelerations. Applying the Fourier transform to both sides of this equation, because of linearity, the 1 over c squared will come out, and we'll get the second order time derivative of u hat. We get over here I times s squared times u hat. So now we solve for this ordinary differential equation in t. So we have then u hat tt is minus c squared s squared u hat. We also have the Fourier transform that we can apply to the initial data, and that gives u hat of blank 0 equals u hat naught. These will be functions of s now, and over here u hat t is u naught hat t of that new variable. It will be dependent upon s. Holding s constant, we see that the wave equation transforms into this second order ordinary differential equation in t, holding s fixed, where u hat, if s is fixed, will be a function of t. What function has second order derivative equal to the negative times a constant times itself? Well, clearly u hat will be a constant times cosine of CST plus another constant times the sine of CST. Those are the functions that have derivatives equal to the negatives of themselves. Here we have to assume that C1 is constant relative to t, but it could be a function of s. Same thing with C2. These could be functions of s. It's at this point that we account for the initial data. So u hat naught is going to be what we get when we plug in t equals 0. Well, sine of 0 is 0, so we get C1 of s. Down here, u hat 0t is what you get when you take the derivative of this and then plug in 0. When you take the derivative of cosine, you get negative sine with a cs out front, but evaluated at 0, you still get 0. Over here, when you take the derivative with respect to t, you get a factor of cs by the chain rule times c2. And so the cosine evaluated at 0 will be 1. You end up with cs times c2 being the initial velocities. Writing this out then, u hat is going to be u naught hat times this cosine of CST, and solving for C2 we'll have u hat naught t divided by CS times the sine of CST. It's at this point that we recover u by performing the inverse Fourier transform. And so we'll integrate e to the ISX times the function that we have here, we integrate out s, leaving then a function of x and t. It can be shown that this integral results in the D'Alembert solution. Eventually. As our next example, let's look at the one-dimensional heat equation on an infinite rod. So x's will go between minus infinity and infinity. So for the heat equation, I'll write 1 over c squared ut equals uxx with our initial data. Like this. We'll apply the Fourier transform to both sides. And we'll have an is squared because of the second order derivative with respect to x. This will lead then to u hat t equals minus c squared s squared u hat. And that implies then that u hat is of the form e to the minus c squared s squared times t. Times, of course, a constant, which I'll put a tilde over to distinguish it from the c, which is a function of s. Applying the Laplace transform to the initial data, we see that u naught hat is going to be what you get when you plug in t equals 0. And so the constant of integration ends up being the Fourier transform of the original data. So we have u hat is u hat naught of s, e to the minus s squared c squared t. To recover the solution to the heat equation, all we have to do then is apply the inverse Laplace transform to both sides. It implies then, using the normalization constant that we talked about earlier, that u is 1 over root 2 pi, integral from minus infinity to infinity, u naught hat of s, e to the minus s squared c squared t, e to the positive s x times I ds. And we'll complete this later. Let's do an example where maybe we can run this to completion. We'll start off with a second order partial in this form with data the square root of pi over 2 times e to the minus absolute value of x, killing this off in both directions. We'll apply the Laplace transform to both sides. On the left-hand side, we'll have is u hat t, and on the right-hand side, it's is squared u hat. We can cancel one of the is's off on both sides. We're looking for the solution to a differential equation where the derivative of the function is a constant times itself. Well, that means u hat must be of the form some constant times e to the is constant t. And now we need to be sure that the initial data holds. So we need to know the Fourier transform of the initial data. So we'll have 1 over root 2 pi root pi over 2 e to the minus absolute value of x e to the minus I s x dx. We'll have 1/2 the integral from minus infinity to infinity. We have this e to the minus absolute value of x, which is an even function, but it's being multiplied by cosine of is x minus I sine of sx. Oops, no I here, using Euler's formula, and then dx. The second term is odd relative to x, and it follows then that its integral will converge to 0. So we only have to deal with this first part, and there we can double the integral from 0 to infinity. That allows us to get rid of the absolute value cosine sx dx. We'll have to calculate this integral, which I'll denote by I, using integration by parts a couple times, so I'll use the tabular method. There's a u and a dv. It doesn't really matter which you take for u and which you take for dv. I'll take u to be cosine of sx and dv to be e to the minus x dx. We'll take the derivative down the first column, that's minus s sine of sx, and integrate down this second column, and so we'll get a minus e to the minus x, because you divide by the -1. And we'll have to do this again. So we'll have minus s squared cosine of sx and a plus e to the minus x. So we'll multiply down diagonals and alternate signs, plus, minus. We'll have to, since we don't terminate in 0, subtract the integral and affix the sign from above, which in this case is a minus. And so we'll have the following. This product, minus cosine sx e to the minus x, 0 to infinity. And then minus a minus is a plus s sine sx e to the minus x. And then we subtract the integral of the product, which also has a minus, and then affix the minus sign here. So that's 3 minuses. The s squared can come out, and so the last term is going to be a minus s squared times capital I. What about the other terms? Here, as x goes to infinity, e to the minus x goes to 0, killing this off, and when we plug in 0, sine of 0 is 0, so this term contributes nothing. This term does contribute something, not as we go to infinity, but as we subtract what we get when we plug in 0. And so when we subtract what we get when we plug in 0, we'll have a positive 1. We'll have minus s squared times I, all equal to this integral I. We'll have to move the s squared I over and have 1 plus s squared I equals 1, which means the original integral is 1 over 1 plus s squared. And so the Fourier transform that we seek is 1 over 1 plus s squared. By the way, if you get some of these integration tricks that I'm trying to train you, it will really help you speed up your computations in the future. So this was the initial data with the Fourier transform applied. Now we had u hat was some constant of s e to the is t. But we have to have u hat naught of s be what you get when you plug in t equals 0. So the constant function out front is the initial data with the Fourier transform applied, which implies then that u is u hat naught of s e to the ist. All we have to do now is undo the Fourier transform in order to recover u, which looks like it should be pretty easy to do this time. We have 1 over 1 plus s squared e to the ist, which means that u is going to be the inverse Fourier transform of all of that. So we'll get 1 over root 2 pi, the integral from minus infinity to infinity of 1 over 1 plus s squared e to the ist times e to the isx dx. We can rewrite this with an is times t plus x. And this looks like a translation of the data that we started with. Like this. So if the initial data looks something like this, the only thing that will happen is, since we're adding t, is a translation negative t units to the left, or t units to the left in this case. In our next example, we'll apply something where the when a partial differential equation applies to the torque on a bar. With some initial data, applying the Fourier transform, we're looking for a function with second order derivative equal to is to the fourth times itself. I to the fourth is 1. And so this is s to the fourth u hat. So we're looking for a function with second order derivative equal to s to the fourth times itself. And this being positive now, functions which have second order derivatives equal to the positives of themselves are like hyperbolic sine and hyperbolic cosine. Derivative of cosh is sinh. Derivative of sinh is cosh. So second order derivative of cosh is cosh. Similarly, second order derivative of sinh is sinh. So you might suspect that u hat would be some c1 of s cosh of s squared t plus c2 of s sinh of s squared t, but this would be a bad choice of solution basis for the original differential equation. And the reason that this is a bad choice is that both cosh and sinh are not integrable. They're not bounded as you go off to plus and minus infinity. So these are going to be very poor choices for basis. There is an alternative basis, and that's e to the positive constant times t, which has second order derivative to a constant squared times e to the constant times t, and also e to the minus constant times t, because two order derivatives, you get two negatives, which cancels out. So you could look at it this way. U hat is c1 of s e to the minus s squared t plus c2 of s e to the plus s squared t. But one of these terms is also not permissible, and that's because as t goes to infinity, this second term also blows up. So this term has to be out by boundedness. For boundedness considerations, we'll only end up with this first term. Now we have to apply the initial data to uncover C1 of S. So clearly, u hat is going to be u hat naught e to the minus s squared t, where at this point we apply the inverse Fourier transform. We have then, using our normalization constant, we'll integrate from minus infinity to infinity u hat naught of s e to the minus s squared t e to the positive I s x ds. There's really nothing more we can do with it at this point until we figure out what our initial data really is. In our next example, we'll look at t ux plus ut equals 0 with u of x0 equals u naught of x. Applying the Fourier transform to both sides, we'll have ist u hat plus u hat t equals 0, so that u hat t is minus ist u hat. To solve this ordinary differential equation, we'll separate variables by dividing the u hat off and integrating with respect to t. So we'll have log of u hat equals minus ist squared over 2 plus some constant relative to t, but not necessarily relative to s, and then exponentiate to get u hat is some constant function of s times e to the minus 1/2 st squared. Of course, implying the initial data, we'll get u hat naught of s e to the minus 1/2 st squared as the solution. We just need to calculate the inverse Fourier transform. And I left off the i's on each of those, but u will be the inverse Fourier transform, which is 1 over root 2 pi integral from minus infinity to infinity. We'll have u hat naught of s e to the positive I s x times e to the minus I over 2 st squared ds. And you can see then we'll have a translation the x variable translation by 1/2 t squared to the right of the inverse Fourier transform of u hat, which is u naught, evaluated at x minus 1/2 t squared. So the effect of our differential equation t ux plus ut equals 0 is to take the initial data and translate it at an increasing rate to the right. We're next going to talk about the Dirichlet problem, and the Poisson integral formula. the Dirichlet problem, you'll recall, where we assume that the Laplacian here is uxx plus uyy, with the initial data being some arbitrarily defined function at y equals 0. This is going to be defined on the points x, y lying in the upper half plane. So we're requiring the y coordinates to be positive with the boundary at y equals 0. We're going to define something called the Poisson kernel. Py of x is going to be defined by, we're going to have this factor root 2 over pi times y over x squared plus y squared. After a short computation, it follows that p hat y of s is e to the minus y absolute value of s. It follows then, considering our original PDE, Laplacian u equals 0, taking the integral with respect to x, which goes from minus infinity to infinity, we'll have 0 equals minus is squared u hat plus u hat yy. This yields the differential equation u hat equals s squared, u hat yy equals s squared u hat, and the derivatives being with respect to y, we end up with a basis of either cosh of sy and sinh of sy, or e to the positive sy and e to the negative sy. Now, we can't use cosh and sinh because both of those functions are unbounded. So we end up with c1 of s e to the minus sy plus c2 of s e to the positive sy as our solutions. And the second coefficient must in fact be 0 by considerations of boundedness. And this first coefficient ends up having to be the Fourier transform of the initial data, because of the initial data. So we have then u hat is u hat naught of s e to the minus sy, which is of the form function of s times a function of s. You'll recall that if we take the inverse Fourier transform of the product of two functions, we get the convolution of the corresponding un-Fourier transform functions. It follows then that u is the convolution of the Poisson kernel convolved with our u naught. So what does this give? You'll recall that we're using a normalization factor of 1 over root 2 pi. We'll be integrating from minus infinity to infinity. Py has a factor of root 2 over pi out front. We'll of t y over x minus t quantity squared plus y squared dt. With respect to this integral, since we're integrating on this t, this y can come all the way out front. The root 2 can cancel with the root 2, and we'll just end up with a pi out front, combining the two root pi's. All that remains in terms of solving this Dirichlet problem is to specify the initial data and calculate the integral. In this way, this method gives us the solution to all of these problems. So this is a nice way of solving a whole class of problems in one fell swoop. I wish to define something called Gauss's kernel, or the heat kernel. It's going to be defined to be 1 over c root 2t times e to the minus s squared over 4 c squared t, where it can be shown that the Fourier transform of gt is e to the minus s squared c squared t. And it follows immediately then that the solution to our heat equation is going to be our initial data convolved with the heat kernel, giving you a beautiful solution to an entire class of problems. We're going to define the error function which has the notation ERF of s. It's going to be 2 divided by the square root of pi, integral from 0 to s, e to the minus z squared dz. So you can see here this is equivalent to taking our usual Gaussian curve and integrating from minus s to s to get the area under the curve. We're integrating from 0 to s and doubling that, but it amounts to the same thing as integrating with a 1 here and from negative s to s. Let's look then at a heat equation with c equal to 1, but the initial data is defined to be, let's say, 100 between negative 1 and 1 and 0 otherwise. What do you expect the heat equation to do? Well, you kind of expect this heat to diffuse outward and the center to remain hotter than the boundary edges. But we can get the solution very simply by taking the initial data and convolving it with the Gaussian kernel. So U is U naught convolved with the Gaussian kernel. So for the convolution, we'll have a 1 over the square root of 2 pi. This u will be 0 outside of the interval from negative 1 to 1 and 100 otherwise. So now we just have to deal with this translated Gaussian kernel, or heat kernel, which is 1 over c, c being 1, root 2t, e to the minus x minus s quantity squared over 4 c squared is 1, t, and then ds. You can see then that these root 2's will combine and become a 2, so we can cancel that and put a 50 in this spot. The question now becomes, how do we deal with the integral that remains? Well, we have the following substitution presents itself. X minus s over 2 root t. If that's true, then du is negative 1 over 2 root t ds. And we'll use this to transform our integral. Let's see, we have 50 over root pi integral. The limits of an integration transform will have x plus 1 over 2 root t, and then at 1, x minus 1 over 2 root t. We'll have a minus here. We'll use that. We'll take care of this minus later by reversing the order of integration. We'll still need a 2 down here, so we'll put a 2 here and a 2 here. 2 root t ds. So we'll still have this 2, and then we'll have e to the minus, I guess I should call this a w because we are already using u, squared dW. So it looks like we'll have a 100 over root pi here, and well, it looks like we have something like a Gaussian here. Remember, the Gaussian had 2 over root pi, so I'll put that 50 back and put a 2, so I have 2 over root pi. We'll have the Gaussian. Normally the Gaussian was integrated from 0 to s, but now it's integrated from negative s, or negative a to, from a to b instead. One way of dealing with that is breaking this up into integrals from a to 0 and then from 0 to b. Either way, what we're getting here is 50 times the difference, and reversing the order of integration and changing the sign, we get the error function evaluated at x plus 1 over 2 root t minus the error function evaluated at x minus 1 over 2 root t as the solution to this heat equation. So you can see we're getting the movement of these boundary parts. We kind of think of this square root of t as being like the standard deviation, and so what happens as time goes along is that standard deviation becomes larger and larger. You can see then that I've taken the liberty of typing in the commands to produce the animation. Here we have the initial data, or close to the initial data. Notice I'm starting at time a little bit bigger than 0 because of this division by 0 that we'll get. But now if we press play on the animation, you can see how the region spreads out. And so I'll put this on a continuous loop so you can see this initial data spreading out down the wire, and the peak energy going from 100 to lower, but the region where the temperature spread out gets wider and wider.